Hello everybody, and welcome to the next video on functions. In this video we will cover one of my favorite function topics to cover, and that topic is recursion. Recursion is just a really adorable idea, first and foremost. I really like the idea of it, the concept of it. And secondly, it can do some nice things for you. Okay, it can do some nice computational tasks for you. So it works on sort of both levels. It's a nice idea, it's nice to think about, and it does some nice tasks for you. So in this video, I'm going to do two things. I have to tell you what recursion is, first of all, and then I want to illustrate it with two examples, one that calculates Fibonacci numbers. So if you don't know what those are, I will tell you. And another recursive function that reverses a string. So you input a string, and the function gives you back all the letters reversed. So let's start with the idea of recursion. So recall from a previous video and previous examples that functions can call on other functions if they want to. So this is a function from a previous video. It was a perfect number calculator within a given range. So you input A and B, and what this function did for you was calculate all perfect numbers between A and B, and then returned that as a list to you. So recall exactly how this function worked. It started with an empty list, and then you let k range from A to B, and then if k was perfect, you appended it to this list, and then in the end you returned that list. Okay, recall that this right here, is perfect k, is perfect was its own other function that we wrote and put above this perfect numbers function. So perfect numbers called on or used another function. And that's fine. You know, functions can use other functions if they want to. So this leads to a question though. Could a function use itself? So can a function call on itself within itself? It seems like kind of an odd thing to do, but the answer here is yes. A function can call on itself. It can reach within itself and use itself as part of its task. Any function that does that is called a recursive function. Okay? So one of the reasons that recursive functions are so nice is that because they're self-referencing, they use themselves like this, they're kind of like fractals, if you know what that term is. So a fractal is like these really beautiful pictures that contain themselves within themselves. So you keep zooming in, zooming in, zooming into the picture, and you keep seeing the same picture within there. These functions are kind of like that because they contain themselves within themselves. So they're kind of like snakes eating their own tails, maybe, right? They feed on themselves. So to illustrate this concept, let's do our first example, the Fibonacci numbers. So these are the Fibonacci numbers. They are a list or a sequence of numbers, and they start 1, 1, 2, 3, etc. And notice that any number in this list, like say 5, is the sum of the previous two numbers. So 2 and 3 make up 5, 5 and 8 make up 13, etc. So at any point in this list of numbers, whatever number you're looking at is by definition the sum of the previous two. That is how the Fibonacci numbers are created. So what I want to do is build a function that returns the nth Fibonacci number. In other words, if I input a 1, I want the function to give me a 1 back because 1 is the first Fibonacci number. If I input a 2, I also want a 1 returned because 1 is also the second Fibonacci number. If I input a 3, I want a 2 back. If I input a 6, I want an 8 back, and so on. Okay, so I input where in the sequence I want it to look, and then give me back the number at that spot. And notice, by the way here, this is a function I'm creating, so I can decide to start counting at 1 if I want to. So if this were a literal list saved in Python as a list, then this first 1 would be like the 0th Fibonacci number. It would be in position 0. Okay, but again, I control this function. So if I want to think of this as position 1 and the first number, then I can do that, and so I will. Okay, let me show you a function that creates this sequence. So on input of a number n, let's just walk through what this function does. Well, if your input number was a 1, then as we already said, you should return a 1, because 1 is the first Fibonacci number. So if you input a 1, give me a 1 back, please. Otherwise, if I input a 2, you should also give me a 1 back, because 1 is also the second Fibonacci number. Okay, now notice, there's nothing particularly new or revolutionary about those lines of code, but notice what happens here in the else statement. What if I entered something that wasn't 1, wasn't 2? What does this function do? It eats itself, okay? It reaches within itself. It calls on itself. What it does is it takes that in value, knocks it down by 1, and feeds that back into itself. Takes that in value, knocks it down by 2, feeds that into itself, and then adds the result. Which, if you think about it, makes some sense, right? Because again, a given Fibonacci number, it is the sum of the Fibonacci right before it and the Fibonacci twice before it, right? So in terms of position, right, this is the 7th Fibonacci number. It is the sum of the 6th and the 5th Fibonacci number. Okay, so let's walk through this function and see precisely how it's doing its task. So, first question, what is Fibonacci of 1? You input a 1, what comes back at you? Well, as we discussed, a 1 comes back. That's been hard-coded in there, right? If the input is 1, just give me a 1 back. What if I input a 2? Same thing. If n is 2, just give me a 1 back. That's hard-coded in. Okay, what if you input a 3? What happens here? Well, 3 is not 1, 3 is not 2, so you must go into this else. And now in this else, it says, hey, return Fibonacci of 1 less than 3. So a 2 right there, plus Fibonacci of 2 less than 3. So a 1. Okay, so what gets written is Fibonacci of 2 plus Fibonacci of 1, but the computer knows what those are, right? Fibonacci of 1 was 1, Fibonacci of 2 was 1, so it just does 1 plus 1, because it knows what these return values are here, right? We hard-coded that. So, in general, this is how the function will handle Fibonacci of any number. So what about Fibonacci of 5? How does it handle that? 5 isn't 1, 5 isn't 2, so it must go down here. And now 1 less than 5 is 4, so it puts a 4 right there. 2 less than 5 is 3, so it puts a 3 right there. And then just sort of a chain reaction gets set off here. Fibonacci of 4, right, the 4th Fibonacci number, plus the 3rd Fibonacci number. Well, the 3rd Fibonacci number we already have recorded here, right? It's 2, so there's just a 2 right there. How does the function handle Fibonacci of 4? Well, 4 is not 1, 4 is not 2, so we're down here in the else. You're going to return now 1 less than 4 right here, 2 less than 4 right here. So Fibonacci of 4, by definition from the function, is the 3rd Fibonacci number plus the 2nd. And now, right, we started with a 5, and now Fibonacci of 5 has been written like all this. All this highlighted stuff involves inputting a 2 or inputting a 3 into the function, and we know how the function behaves there, right? If you input a 2, you get a 1 back. It just says so, right? If you input a 3, we know you get a 2 back, because we already did that computation. Okay, so when you send a 5 into the function, again, it's like a chain reaction or a chain of dominoes falling, right? The function says, I don't know how to deal with 5, right? Because 5 falls into this case. I don't know what to do with 5. Okay, so what I'm supposed to do, though, is feed 4 and 3 into myself. Oh, but I don't know how to deal with 4 or 3 either, because the only hard-coded values are 1 and 2. I don't know how to deal with 4 and 3, so now I got to feed those back into myself, knocking them down by 1, and so on. So you reach a chain reaction back to sort of the foundation of the function, and then from that you can sort of build up the eventual output. So let me just show you one more time with a bigger one. The 7th Fibonacci number, how does the function handle that? Well, it feeds back in on itself the numbers 5 and 6. But how does it handle 6? How does it handle 5? Well, it just feeds those back in on itself. The 6th Fibonacci number is the 5th plus the 4th. The 5th one is the 4th plus the 3rd. And then now, just to save myself room on the slides, I abbreviate Fibonacci to F. Okay, you can't do this in the code. I'm just doing this to fit on the slide. What's F of 5? Well, it's the fourth plus the third, you know. What's the fourth? It's the third plus the second. Fourth is the third plus the second. Third is second plus first. And you just keep going, right? And eventually notice, right, you end up at a point where all you have are 2's and 1's. So there's an f of 2, f of 1. Here's an f of 2, which the function knows how to deal with. There's an f of 3, f of 2, f of 3, 3 and 4. So what? Half of the quantities here, the function knows precisely what to do with. Any input of 2 gives you a 1. Any input of 1 gives you a 1. These 3, 3, 3, 3, and then 4, those get decomposed even further. I don't have room on the slide to write all of it, you know, but you just keep decomposing until you end up with return values that you recognize. So again, it just sort of sets off this big chain reaction, right? Things just keep getting like exploding, you know. So 7 gets split into 2 pieces. Each of those gets split into 2 pieces, right? So on down. But eventually, you can just return a number. And that number is this big old sum here, you know, once you've actually figured out what f of 4, f of 3 are. Okay, so that's how the Fibonacci calculator works. Let me just show you in the compiler what you can do. So there's the function, you know, so I can just ask it like, hey, print for me Fibonacci 4. What's the fourth Fibonacci number? So I do that, and it prints 3. Which, if you recall, was indeed the fourth Fibonacci numbers. The Fibonacci numbers go 1, 1, 2, 3. And I can ask it, hey, what's the sixth one? I don't know. It tells me 8. And that was indeed the sixth Fibonacci number. I can like tell it to print a bunch of them for me. So maybe start at the first one and print all the way to the 10th one or something, you know. So print for me the first 10 Fibonacci numbers, and it prints them. So 21 was the last one we saw on the slide. The next one is 34, because that's 21 plus 13. And you could like do this some more if you want to, right? Like ask it to print the first 25 Fibonacci numbers. And they start to get pretty big, you know, because you keep adding previous ones together. But the 25th Fibonacci number is about 46,000. And the sequence starts as it always starts, right? 1, 1, 2, 3, 5, whatever. Okay, so there's our first example of a recursive function, a function that feeds on itself to create this sequence. I guess I should say, right, that the Fibonacci sequence of numbers, mathematicians call those sequences recursively defined because a given number in the sequence depends on previous numbers in the sequence. Right? So wherever you are right now, it depended on the values of the 2 previous numbers. Any list of numbers like that is called recursively defined in mathematics. So it is perhaps not surprising that recursively defined sequences can be computed using a recursive function. Okay, so now let's do an example that has really nothing to do with math at all. It's a function that returns the reversal of a string. So if you input the word back, then the function gives you back cab, right? The letters have been reversed. Let me show you a recursive function that does this. And I guess I should say that this function here, many of you are probably able to come up with a non-recursive function to do this task. But I show you a recursive one just to illustrate recursiveness. And also, this recursive function is pretty short. So let's just think about how you would do this task recursively. So I'm going to build a function called reverse, and I'm going to input a string. Whoops, sorry, this should say my string here, right? Sorry. Yeah, my string, my string, my string. So this should say my string right here. So anyway, if you think about what's happening here, if the input string, my string, if that's the empty string, so there's nothing to it, you know, no characters, you should, of course, return the empty string because the reversal of nothing is still nothing, you know. So if there are no characters, then you just return the string with no characters in it. Otherwise, though, what if the string has some characters to it? Then I'm going to pluck off the first character that I see. So when I first see back, right, I should record this B. And then notice what happens here. I'm going to feed my string without its first character in it, right? So recall this command here, this one-on command. This starts at position 1 and then goes until the end of the string. So my string and then 1 colon. That's all the characters of the string except for the first character, the character in position 0, which, by the way, I recorded here, right? So first character is what's now missing from this, okay? So you take the entire string except for the 0th character, or the first character, however you want to say it, and you feed that back into the function itself. But notice what you do. You tack on, you add that first character to it. So recall, the addition with strings, it just tacks something onto the end. Okay, so this reverse blah blah, right? That's a string itself, and you're just adding something to the end of it. So on the first pass through of this function, what happens? You feed in the word back. Well, back is not empty, right? So you land yourself down here in this else. First character is B. So I record a B. And then I return reverse my string with that B missing, right? So this now here is ACK. It's just ACK. But you're adding a B to the end of it, right? Okay, so now ACK gets fed in. Well, ACK is not empty, so I record the first character of that. Well, the first character of ACK is A. So now I feed in just CK into this, right? I pluck that A off now, put the CK in there, and I add the A to the end. But recall, I've already added a B to the end, So I've recorded a B at the end, then A comes next, and then so on. So this process just keeps iterating until you have nothing left when it stops. It just returns nothing at the end of it. So you just exhaust the string. So all this English here just says everything I just said. So how does it handle ACK? Well, it records the B, then feeds ACK back in, adding B to the end. Then it sees the ACK, records the A, feeds CK in, right, etc. The next thing it'll do is see the CK, record the C, add that, and so on. So you keep going until the string is done. So let's just quickly implement this in the compiler. I think I have it somewhere. Okay, here's the function. Whoop. Just put it up here over the Fibonacci. So it's just the same thing from the slides. So now I could ask it, hey, what do you think the reversal of, well, let's do back, right? Reverse that string for me, please, and tell me what it is. And notice it prints KCAB, What if you make this bigger? I don't know. All right, let's see if it can reverse that. And it can, right? Erutuf et ot cab. Okay, so, recursion, like many topics in programming, takes some getting used to, So writing a recursive function on your own is not an easy task, especially at first, but hopefully these examples are illustrative, and hopefully that seeing these examples helps you write your own when we meet in class.